Hello, everyone. This is Michael E. Yeaman with another Geology of Sculpting Stone. Today, we're going to talk about Indiana Limestone. But why should you even care about the geology of your stone? We know stone sculpture is one of the few art forms that date back to the very beginning of history. The story of our stone is unique. To know more about the geology of your stone will allow you to select specific stone types that have a compelling history for both you and your viewer alike. You can marvel at the stone's various elements, its color, texture, composition, grain, all while you're working it can make working even more interesting. You can consider how the sculpture's form, your chosen artistic form, relates to the science of the stone. And finally, you can weave into the final artwork a story, a geologic story component that enhances the interest of your work for both yourself and for your potential buyers. So, as usual for these presentations, we have an outline. Outline's made of three elements. We're going to define a little bit about the stone. It's a little bit general description, physical properties, chemical, its historic use, what it looks like both in large scale and in thin sections, specific occurrences. Then we'll talk a little bit about its geology, age, and its geologic description, what environment the stone was actually formed in, where it was formed in the world at the time, the paleogeographic setting, and are there any modern analogs of where you might find the stone being formed today? And then finally, we'll take a look at select creations, both artistic and architectural. So first of all, general description. So Indiana limestone is the common name given to the Salem formation of limestone, which is a fine grain, usually buff or tan and gray in color, and outcrops out in southwestern Indiana. Where it's quarried, it's about 8 to 18 meters thick, which is actually quite thick and convenient. It's quite massive in the sense that it doesn't have a lot of specific bedding planes or other symbols like stylites, pressure dissolution surfaces, or other things that would perhaps mar its overall clean appearance. It's chemically pure. You can see the chemical composition to the right. It's almost entirely all calcium carbonate with a little bit of magnesium and aluminum oxide and a tiny bit of gritty SiO2 silica. When it's quarried, it's actually quite soft, and then when it hardens, or when it sits out, I should say, it actually begins to case harden, making it more resistant to weathering, which is actually a very preferential character. It has no strong direction of cleavage, and therefore it can be easily shaped by hand or machine in just about any form. Finally, quarrying began in the Indiana limestone back in 1927, and was by the end of the mid 1800s, it was going to be used outside of the local area as railroads arrived in the area. And then by 1900, believe it or not, Indiana limestone represented a third of all the U.S. dimension or stone used for building, which increased that to 80% by 1920. Can you believe it? 80% of the dimension stone used for building by 1920 was Indiana limestone. Very, very, very popular. And currently, there are still 9 active quarries producing over 76,000 cubic meters of Indiana limestone every year. Now let's take a look at some pictures of the Indiana limestone. First of all, here is the outcrop of it. You can see it's clean, massive characters, no significant bedding planes. The weathering surface shows some water, obviously, and some minor plants, but it's a nice blocky stone for quarrying. In hand specimen, here it is, and it's more grayish form. It doesn't have any pronounced flat surfaces that would suggest a natural cleavage direction. If we get down to rough blocks, now the rough blocks have been split into specific blocky characters. You can see some of the drill holes used to pry out the block from the outcrop. And then finally, here are the prep blocks and slabs ready to load up on trains and head off to either quarries or your sculpting pad. Now, specimens. Now, specimens, besides, of course, the big macro ones, are oftentimes produced in very thin pieces for geologic analysis. We call them thin sections. Now, here are some black and white photographs of thin sections cut very thin so that when you shine light through them, you can actually see some distinct characteristics of the rock. The upper ones show something called oolids, which are small grains or old small shells which have been rolled around in the surface of a shallow marine environment. And some of them you can see on the left have begun to squeeze together. And on the right, you can see the wide variety of individual shells that make up the Indiana limestone, a wide variety of little small micro shells of creatures who lived at the time. Down below, you can see different characteristics of some of these shallow water environments, from high energy to shoaling environments to back shoals, intershoalar facies, all of which produced slightly different little small fossils, each with their own individual shell type. Quite intriguing when you see these things in thin section. Now, specific occurrences. Well, as I mentioned, the Indiana limestone occurs in southwestern Indiana, and here it's a location map extending in a north-south line all the way from the White River down to the southern border of Indiana, with a lot of spots where the Indiana limestone comes quite close to the surface, outcrops, what we would say, and that closeness of the surface makes accessing them for quarrying quite possible. By the mid 20th century, quarrying was still extremely active in the Indiana limestone. Old hand drilling techniques to drill the holes that would be later used for splitting the blocks away from the surface. Some old cranes and other surfaces that were used for lifting the big blocks out of the quarry. Some of these were even originally steam powered. And then finally, active modern quarries include same cranes, all gasoline, diesel nowadays, still sculpting quite close to the surface. You can see the trees growing right on the surface of the outcrops, so quite strong and quite active still today and actively used in building. So let's talk a little bit about the age and geologic description of the Indiana limestone. Well, the Indiana limestone was formed about 340 million years ago during a time in the Earth's history that geologists, at least in the United States, like to call the Mississippian. The general area of the Indiana limestone is made up of three major limestone formations, the bottom one being the Harrodsburg limestone, the central one being the Salem, and then the upper one being the St. Louis, all limestones. But the formation we want to focus in on is the Salem limestone formation, about 20 to 30 feet thick, 20 to 80 feet thick. It's bluish, gray to buff, cream colored throughout most of it. It's fairly evenly grained, porous, massive in the sense it doesn't contain a lot of layers. There's a little bit of cross-bedding in it, but it's fairly subtle. And there's also abundant small fossils and fossil fragments we found and we saw in those thin sections just a minute ago. Now, we want to talk a little bit more about the age and geologic description of the Indiana limestone. And in that, I was able to find this wonderful old photograph, probably from the mid 20th century, of a section through an old quarry. And you can see here in this section, I'll highlight it here in red, there's the Harrodsburg Formation down below, the Salem here in the middle, and then find the St. Louis Formation on top. And you can see the area what they label building stone in this old photograph is the section that would be where they would have pulled most of the big blocks of the Indiana limestone. Here's one of these old quarrying cranes, a section of it there in the background. And also here on the far right, you can see where the sun shining on the face of this big block of limestone, how massive it is with very few layers, unlike the limestone above and below it. Finally, if we close out with a little bit more additional description of what the Indiana limestone is, geologists would refer to it as a cross-bedded calcarenite, being medium to coarse, and as we said, tan to gray. It would be kind of gritty in your hand, like a gritty piece of sand if you ground some up. It occurs in these exceptionally thick beds, specifically within the Salem limestone, and as I mentioned before, it's internationally known for being a great building stone. As we saw in the thin sections, many of these areas in the Indiana contain these small rounded shell tests, which were produced by a life form called foraminifera, quite active and widespread in this section 340 million years ago, the Middle Paleozoic. In addition, some of the other lithologies include a little bit of shale, not much though, some other types of limestones, including a little bit of argillaceous dolomite. That's the magnesium we saw in that chemical formula a few minutes ago, and includes many places where these oolites, these rounded little shell tests, which are quite pretty in cross-section, occur. Now, I found to display the characteristics of the Indiana limestone a great diagram that talks about the depositional or formation environment. And so let's talk about that and some of the processes that would have gone on. So the Indiana limestone would have formed in an environment of a shallow marine ramp. This is what you see here, a picture of what's called a shallow marine ramp. And they occur in many places of the world. We'll talk about specific occurrences here in a minute. But in ideal sense, they go, and this diagram shows here, I'll draw a little line from the upper right to the lower left, an area where you have shallow water, maybe a sandy beach made up of these little calcareous tests that will be rolling around on the beach, shallow water in front of it, maybe some places it might have a lagoon. And as you get into deeper and deeper water, as you move out into the deeper water that would be in the marine environment, the ocean environment to the lower left, you begin to move into this area called a restricted marine ramp. Now, you can see here as a cross section here, I'll do a vertical line. This is a cross section like we were looking at here a few slides ago, where you look at a cross section of different types of, in this case, limestone that's being deposited, or soft sediment that's being deposited that will be converted into limestone with pressure and time. And there's various definitions down here at the bottom that geologists use to describe the sorting and the type of individual calcium carbonate fragments you'll find in this environment. So in general, we believe the Indiana limestone formed in a shallow water environment, ranging from a shallow and sandy beach out into deeper and deep water, and ultimately into the deep ocean. Now, if we lay over this some pictures of marine life that would have been around at the time, here we have three pictures of different types of components that would have been growing on the sea bottom or living in the sea bottom, and that ultimately would have made up some of the elements, the calcium carbonate elements that ultimately would have been turned into limestone. They involve these wonderful little creatures up here on the upper right, crinoids. Crinoids are a type of echinoderm or starfish, believe it or not, so they're an animal. They're kind of an upside down starfish with the arms of the crinoids being equivalent to the arms of a starfish. They were attached to the bottom. We'll talk about them a little bit more. And they made up huge forests, kind of like kelp, during the time when the Indiana limestone was deposited. Also, you see things that are brachiopods, clams, and mussels, and various types of shellfish that would have been around at the time, hopefully still tasty, don't know. And then also on the right here, a variety of different snails and snail shells that have been found in the Indiana limestone, including some coral fragments, all of which would have been maybe ground around by the waves and the tides, ultimately producing some of the small shell fragments that make up the Indiana limestone. If we take a look at a subcategory of this, mainly because I simply love crinoids, here's a picture in the lower left of what a crinoid looks like in an idealized form. So it has something called a holdfast that would hold this big creature to the bottom. It has a long column that would be made up of a stem that would be made up of small shells holding the crinoid to the bottom. And here it is floating in the water column above these starfish type multi-arms, which would catch small pieces of drifting food that would float by and drag it into its stomach, which was located at the bottom here in the middle bottom of the flower, quote unquote, portion of the crinoid. You can see that in most limestones, a lot of limestone echinoderms, a type that includes starfishes and our crinoids, oftentimes make up as much as 27% of limestones. They're not probably quite as common in the Indiana, but you still see a lot of crinoid fragments. And finally here you see major Paleozoic crinoid groups. So crinoids were so widespread and occurred in so many different forms. So many are so pretty that many fossil collectors have them in various forms on their shelf as attractive examples of fossils of the time. And then finally here I've put on an artist's rendition of one of these mid-Mississippian 340 million years ago artist creations of what the sea life might have looked like in this shallow bottom. Light coming in from above, a lot of floating crinoid attached to the bottom with these arms waving in the shallow water, capturing little bits and pieces of food with a lot of art that ultimately floating down to the bottom and making up the little sandy bottom we see down here, which ultimately will be turned into the gritty sand and compacted into the Indiana limestone. So let's take a look at the global paleographic setting during the time when the Indiana limestone would have been deposited. What we have here is a map of the globe, front and back side, above, and below we have a map of the continental fragments that would have existed during the Mississippian about 340 million years ago. Now, most of you are familiar with the concept of plate tectonics, that being that the pieces of the Earth, the continents, have moved around on the surface over its 4.5 billion year history. So this is what the world looked like 340 million years ago when the Indiana limestone was being deposited. And scientists have been able to determine fragments of the present continents and where they were located. Here, for example, is something labeled NAM or NAM, and that's where most of the old North American continent was before it was in its present location. So let's go ahead and take a look at a little bit more detail. So here we've zoomed in now to take a look at the continents that were around in this central portion around the equator 340 million years ago. And what I've shown here now is the lower section contains the blowup of that section we saw in the previous slide. That was the ancestral North America. And overlaying it, you can see the outline of the Canadian provinces and the North American states. And you can see now in the upper slide, I've broken out some of the names like Gondwanaland, Laurasia. But here right now, I'm circling in red, is location of modern-day Indiana. And so you can see that based on the colorations here, Indiana lay just north of this oceanic inlet with the shallow sea being right off its southern coast. And that's the shallow marine environment, the marine platform we talked about in the previous slide, where the Indiana limestone would have formed. Finally, in this section, let's take a look at some modern analogs, places where nowadays the environment would be very similar to the environment that the Indiana limestone formed in 340 million years ago. I've chosen three locations: the area off of Central America, the Belize area, the Bahamas platform in the Caribbean, and finally Shark Bay off of Western Australia. In each of these cases, the aerial photograph shows the deepening blue water coming into the shallow water environments of whiter to grayish colors, which would be where the carbonate sand is forming nowadays, much like the shallow water environments where the carbonate sand for the Indiana Formation formed 340 million years ago. So Belize is obvious. Here in the Bahamas platform, you have this deeper water inlet in blue and the shallow water carbonate platform off, in this case, the western coast of the island. And then finally in Shark Bay in Western Australia, from the Indian Ocean shallowing into the shallow water bays of Shark Bay and the sands, carbonate sands being formed here. These are modern analogs and give you a sense of what it would have been like in southern Indiana when the Indiana limestone sands were forming 340 million years ago. Now let's take a look at some art produced from the Indiana limestone. Let's start with some great sculptures. During the mid to late 1800s, as we read, a lot of Indiana limestone was used in architectural but also artistic sculpting environments, especially in the Midwest and the East Coast. Here are three examples, one from the Department of Commerce, some bas relief, Also, some bas relief from an Art Deco feature of the Rockefeller Center, and this beautiful sculpture here, making up most of the front facade of the Grand Central Terminal in New York, of these wonderfully carved figures representing, I think, both marine transportation gods and goddesses, but it shows you the wonderful sculpting capability of the Indiana limestone. And then here's a picture of something made by one of us here, Tom Small and I, during 2009. Tom was really getting used to using that wonderful diamond chainsaw set he has, and we had some big blocks of Indiana limestone that summer at camp, and he carved one of his classical geometric angled pieces into a block in a rough form, and then I got it and finished it and polished it and rounded out some elements of it, and then mounted it on this granite base, and it sits in front of my house today. So it's actively sculpted by members of our own NWSSA association, and it's a wonderful stone in many ways because it can be worked by hand tools, by air tools, by electric tools, and it polishes up nicely to this nice, in this case, this nice buff color. If we take a look at architecture, as I mentioned at one time, Indiana limestone was the premier architectural stone in the United States, building things everywhere from palaces at Vanderbilt in North Carolina to large amounts of governmental buildings throughout the United States that was occurring in the late 1800s into the 20th century. And even places like the cladding of the Empire State Building right before World War II, this wonderful hall at Indiana University, which I put on there because I just love the fact that this case, and I think good architecture oftentimes reflects the materials it's made of, the massiveness of this building, a little bit of Art Deco style with its Odeon-esque step-by elements, a little bit of Beaux-Arts perhaps, but its massive style really reflects the block of the Indiana limestone itself that makes it. And I bet all of these walls are load bearing. It's only about 4 stories tall. So this is a great example of the stone speaking to the architecture and vice versa. Let's finish our architecture section by looking at something closer to home, the Seattle Art Museum. It's clad in over 24,000 feet of Indiana limestone, including the massive letters used at the top of the curtain wall. And I think it's a wonderful example of how Indiana limestone used as a structure stone can brighten a facade. In this case, in Seattle, Washington, which frankly, given all of our dark and rainy days up here, is something well worth doing. So in conclusion, what can we say about the Indiana limestone as a sculpting stone? Well, I think it's a wonderful stone in many ways, even though it doesn't have some of the geologic complexity of some of the other stones we've reviewed in this series. And just for that reason, it makes a great stone for particularly figurative carving, but also abstract carving, whenever you want your design to really be the first thing that a viewer sees. By not having the geologic complexity, you're able to observe the form that you've put on your stone with clarity, and you're not being caught up into some of the geologic details that can occur in complex igneous and metamorphics. It has enough interesting geologic history that, especially when you include that in a description of your piece to a potential buyer, that it adds a lot of intrigue, and hopefully this Geology of Sculpting Stone Indiana Limestone presentation has been a valuable tool for you to use in conversations about your stone going forward. We'll look forward to speaking with you next time about another stone that we choose for sculpting. Talk to you soon. Bye-bye.